Good afternoon. Thank you for joining for webinar number 6 in our refrigerant webinar series. We will be starting shortly. We're just waiting for more folks to join. Good afternoon, and thank you again for joining us. We'll go ahead and get started, although I think there are a couple of people still coming on in. Firstly, I wanted to welcome you to the A2L refrigerant behavior in a structure fire discussion. UL expert George Hunter is with us again to share the preliminary results of that project. Before we start, I would like to introduce Steve Urich, the CEO of the Air Conditioning, Heating, and Refrigeration Institute, AHRI, to welcome you all to the 6th installment of the Safe Refrigerant Transition webinar series.
Thank you, Helen, and good afternoon. Welcome to the first 2021 webinar to help safely transition to the next generation of refrigerants. AHRI is hosting these discussions to disseminate to the broadest audience that we can what we have learned from more than $7 million of research that has been funded by AHRI, by DOE, by CARB, and others. The AHRI Safe Transition Task Force is comprised of more than 200 members from more than 75 organizations. This task force is open to new participants from any interested organization, as are these webinars and the task force's website. We're doing this to make sure that all stakeholders have access to the latest technically sound research and information regarding this refrigerant transition. The project that you'll be hearing about today was specifically designed with members of the fire service to develop training for the first responders in case of a fire involving air conditioning equipment or refrigerants. The goal was to gain a better understanding of how a first responder might need to change tactics with new refrigerants. So much of the project compares current refrigerants with their potential replacements. The results provide a reminder of how important it is to use appropriate protective equipment today and confirms that that same need must be in place tomorrow. It also provides important information to have in any protocols for the fire service to address a refrigerant release. Training based on this research and all the previous research is being created by the Fire Service Research Institute, a nonprofit organization that provides fact-based training free of charge on its website aimed at training first responders. This training is scheduled to be available in the second quarter of 2021. FSRI will incorporate videos from this research project into its training, and AHRI will have another webinar to share the training as soon as it becomes available. We hope you will find today's discussion helpful and informative, and that you will plan to join us for all the remaining webinars in this series. I will now turn the program back over to Helen. Helen?
Thank you, Steve. Thanks for joining us today. I'd like to introduce George Hunter, who's an engineer with UL's Research and Development Organization. He has been the lead investigator in AHRI's 9071 and 2 projects, as well as 8028, A2L refrigerants and firefighter tactical considerations, which he'll be talking about today. Chief Bill Offerman has also joined us. He's got 40 years experience in the fire service. He's the fire chief of the Elwood Fire Protection Districts, which I must admit seems to be a very complex district with chemical plants and other challenges. Bill sits on the board of the National Volunteer Fire Council, and he was mayor for 8 years and also sat on the Board of Health for 8 years. Dick Lord is also joining us and works for Carrier Corporation for 47 years and is a senior Carrier fellow in the Advanced Technologies and Refrigerants group, as well as an AHRI fellow. He is a member of the UL 60335-2-40, 3rd edition and 4th edition working groups, and is a consultant to the AHRI 15 and 15.2 committees. He's also a member of the AHRI Safe Refrigerant Transition Task Force and has been involved in many of the AHRTI research projects. With that, George, thank you again for presenting for us, and we look forward to hearing your presentation.
Okay, let me get the technology working here. Okay, that should have it on full screen. So we started this test program, I think back in October, and wanted to be comparing traditional refrigerants like R410A to the A2L refrigerants. So we wanted to have discharges. So the first part of the task was to determine what flow rates we're going to have. So we did that with 4 refrigerants. That involved 19 tests. Scenario 1 was the release of refrigerant using that those same orifice sizes into an open flame. And the second scenario was a leak while firefighters were dancing down a hallway towards a fire room. We skipped scenario 3. Is kind of a very dynamic test program because we learned all we needed to in scenario 3. Scenario 4 was looking at overhaul activities that perhaps results in a line break and what might a firefighter be exposed to. And finally, the last scenario was number 5, was looking at pooled refrigerant ignition. So walking into a room with a pool of refrigerant on the floor, and perhaps some overhaul activity pulls a fire down into that pool. What will happen? So I'll go through this quickly. What we wanted to do was have a 50 grams per second release rate. We tried 2 methods. One was we called a constant pressure, where we had a refrigerant tank filled almost 80%, so that as we're discharging, it's all liquid. The ones that we call a decay, we filled in either 15, 16, 20 pounds, such that about a minute and a half, 2 minutes into that release, it transitions into 2-phase flow. So you have both vapor and liquid coming out of the orifice. So we determined orifice sizes and pressure ranges that we need to achieve that initial 50 grams per second. Just showing you some of the equipment here. We had an S-type load cell, suspended a tank from that. You can see that the tank is wrapped in a heated blanket. We needed that to get up to the pressures that we want. And those you who may know, we are connected to the liquid valve on that refrigerant tank. We did have some safety features installed. Over on the right-hand side is our first remotely operated valve that isolates the tank if we have that need. And on the left side, you can't see the orifice so much, but that left side photo is the actual orifice. We have one manual valve in front of that, and it's just part of our procedure to make sure that we're operating this thing safely. This switch that you see in the center is in a control room so that our operators were isolated from any potential adverse effects of being in the test room. So here's what our spray pattern looked like. The top photo is looking at that initial 50 grams per second release. You can tell by the initial cone there over on the right that it's really, as Dick Lord calls it, it's coming out at the speed of sound. At about 2 minutes is the lower picture where it's made a transition into two-phase flow. And you can see that initial cone is not quite as big, and the flow rate certainly goes down. The graphs on the right side may be a little confusing, but excuse me. After that initial 50 grams per second, we get into two-phase flow, and the discharge rate drops to as low as 5 grams per second. So there's a big difference when we go to two-phase flow. Then we released into an open flame, and I've since updated this slide, but it'll be in the final report. I'm showing, first of all, a constant pressures decay at 6 feet from our sand burner. Then the next block is a pressure decay discharge that's still 6 feet from a sand burner, a flame that's producing 120 kilowatts. And then finally, we did 3 tests at 2 foot distance. And on the right side of the screen, which right now I can't see, trying to move everything around so I can. So we have some difficulties. I didn't want to advance that slide yet, but we have a peak of these refrigerants, and I'm showing the 4th column from the right is the R410A peak, and then this column that says dose, I've really divided that by seconds, and it's somewhere around that's 1707 divided by the duration of 140 seconds, says that the average HF concentration was somewhere around 13 or 12. But then the last 2 columns take a look at what is that peak of A2Ls, which is R32 and R454B. So in some cases they're lower, slightly higher. As far as the relative dose, which really should be the average across the entire 140-second discharge, they're very close. There's not much difference in the concentration of hydrogen fluoride. And the same pattern is true at the decay rate at 6 feet, and also the decay rate at 2 feet distance. This is taking a look at the dose, but it's really just a measure of the average concentration, and the black line is the R410A. That comes all the way up to 1. So I kind of just normalized that. So you can see the R32 was, a little bit higher, R466A a little bit higher, R454B was just a little bit lower, about 10% lower. As far as the concentrations, it's very difficult to make out this slide, but what it's showing is they're really all about the same. This is the instantaneous measurements of hydrogen fluoride concentration using our open path FTIR measurement instrument. Okay, I'm just seeing a note that my internet is unstable, so hopefully you can all still see this. What I'm showing here is a discharge into a 120 kilowatt fire. And what we have is a 3-sided room that's open on where the discharge is. You can see that on the left side of each panel. The top one is R410A. And what we're seeing is that it really is just knocking down the visible size of the fire. We're also measuring heat release while this test is going on. We did not see that this was acting as an extinguishing agent. There was actually a slight increase in the 120 kilowatt fire. Not a significant increase, but it was there. But the effect of this is this discharge stream was cool gas. You see a change in color, but that's really just due to a lighting effect. If you look down in the lower left hand, you see a kind of a spotlight that we used to make sure that the discharge stream was visible, but there was a cone that was in the shade. So that orange color and the maybe bluer color isn't really a change in fire behavior or anything like that. We did not see this discharge get ignited by this sand burner flame, which is running propane sufficient to generate 120 kilowatts. So it's R32 in the upper side. Again, stuff on my screen is getting in the way. So on the lower left is R454B, and on the lower right is R466A. Looks a little different because it's a much denser gas than the other three. But in any case, this is the only effects we saw. It tended to knock down the visible appearance of the flame, but did not increase the fire size that much. This is taking a look at now what we did at 2 feet. We were not able to run R466A because our smoke abatement system wasn't able to scrub elemental iodine from our exhaust stack. So if we do additional testing, we're going to have to figure out how to solve the iodine problem, which is a component in R466A. But you can see there isn't much difference in behavior. The discharge actually shoots through the flame. It knocks down its visible appearance, but it doesn't really change or decrease the heat release rate. It actually does increase a slight amount. So these are some of the observations we have. There's more being developed as I keep working on the report, but this is preliminary results. The discharge at 6 feet with a pressure decay produced more total hydrogen fluoride than releases at constant pressure. That most likely has to do with that period when the discharge rate drops down to less than 20 grams per second, and there's more dwell time of that discharge in the sand burner fire. Both releases at 2 and 6 feet with pressure decay showed more total hydrogen fluoride generation at the 2-foot distance. So we know there was some combustion, some breakdown of the refrigerants, but it just did not result in a visible flame. It wasn't going to look like a flamethrower. Our scenario 2 was to look at much more of a situation that firefighters might encounter. There's a fire in a room, there's a hallway leading down to it, and they're about ready to begin their attack. And we wanted to look at what conditions they're facing. And what I'm looking at is here is peak room center temperatures with the different refrigerants, and a baseline test where we didn't release any refrigerant at all. The temperatures are all above 800 C. And by the way, the melting point of aluminum is 660 C. And I have some photos later on that shows that we definitely melted aluminum components in the air handler. At the door out of the fire room into the hallway, again, we had temperatures close to 900 C. And in the hallway, little mixing with fresh air, so the temperatures were slightly lower, but in the range of 680 to 840. And that, you know, the baseline actually gave us the highest temperature there. The peak at the air handler, we did add some thermocouples to the air handler and attached to the aluminum. You can see that those all exceeded the melting point of aluminum. So finally is the peak heat release rate in kilowatts. And this was more to demonstrate that it was an actual ventilation limited fire. There was plenty of fuel to burn, and in a free burn that we did before we ever started this test series, the same fuel package produced 6,500 kilowatts. So we know that this fire was starved for oxygen and very little oxygen at the ceiling level. So this is now looking at a graph of the 4 different fire sizes, and I'm showing as a messy graph indicating there's not much difference between the baseline and the 3 refrigerants that we tested. The black line that extends more to the right was our baseline test, and we use that to determine when we actually want to release the refrigerant. So we started recording and took idle data or no fire data for 5 minutes, and then we started the fire and found when it got up to its ventilation limited conditions, and we decided that that was at 11, well, actually, what is it? 2, 4, 6, 7 minutes after we started the fire. It's grown to its maximum size, and that's when we decided to release the refrigerant. So what we have done is we release refrigerant outside the unit with R410A and R32, and inside the unit with R32. And we don't see much difference in the heat release rates. That dotted line square is when we actually had the release valve open. So here's a picture of the A coil within the air handler and some locations where we had thermocouples attached, just so we can see what happens with those temperatures. So here's some graphs of the air handler temperatures. You can see the baseline upper left-hand side panel gets all the way above 700 C, and that is just about every location within that air handler. The R410A with a leak outside the unit eventually came to the same. There was a kind of a drop towards the end of that R410A leak, kind of anomalous in that particular case. In the lower left-hand panel was an R32 discharge. And finally, we did a second test with R32, which was inside the unit. And again, we're getting over 700 C. The room thermocouples in our baseline again went up to 800 C. With the R410 leak outside, they didn't climb to the same levels, but the peak temperatures at the ceiling, 92 inches, was up to 900 C. For R32, lower left-hand panels, we had some peaking after we stopped the discharge. So it wasn't the R32 that was involved in that particular peak. Finally, with the inside release, we still saw peaks, you know, in the 800 C range. At the door into that room from the hallway, again, the baseline, we're up to 800 C, and we're seeing similar temperatures based on height. The final test with R32, lower right-hand side, shows very much the same behavior as our baseline test. The other two I'm not quite sure why, but it does make sense that with the fresh air coming in low in the room, that those would stay cool. It's possible with the upper left and the lower right that we just simply had flashover conditions in the room, and it was raising the temperature of everything. The hallway thermocouples were naturally cooler because there's fresh air coming in at the low level, and these lower blue lines show that temperatures stayed pretty low, and the hot gases were coming out high. We still had about 300 C at the 32-inch level. Below that, at the 20-inch level, we were less than 100 C. And that was generally the case in all of those tests. We actually measured the door velocity with a set of 5 bidirectional probes and thermocouples. So what this is showing in every case, there's hot gases coming out of the door and cool gases coming at the lower level. Those heights on those probes were at 6 inches above the floor and 24 inches above the floor. So the hot gas layer was somewhere between 24 and 42 inches, probably more like 30 inches in that range. In the hallway, we're seeing a similar effect. And in this case, we're seeing more inflow coming in at the 24-inch level. And most of the outflow is high in the room at the 60 and the 70-inch level. Those blue lines in the center represent the discharge of refrigerant. So what you're seeing there is not much difference in the flow of gases as a result of discharging refrigerant. And this graph just concentrates on those discharge rates and the mass in the tank. And the little red line is the time when we had the discharge open. So you can see that we've had an initial higher discharge rate at around 50 grams per second, and then it drops down once we go into that two-phase flow region. Heat flux was measured at the entrance to the hallway where firefighters might be staging. We had a few problems with our first baseline test, so it's not really comparable to the other tests. But when we released refrigerant, there were some scattered points up to about 15 kilowatts per square meter. And generally, I would say the average is less than about 8 kilowatts per square meter at the 4-foot level in the hallway. So again, we're assuming firefighters are crouched, preparing to attack down that hallway. So here's some typical photos before the test. Those cardboard boxes are a commodity classification box that we use in sprinkler testing. We have constant heat release characteristics. And so when we burn these in a free burn, we had 6,500 kilowatts. Again, there's a picture of the air handler A coil. And here's some pictures after the fire. We're supported this unit as a ceiling installation. And you can see that the A coil has translated. The unistrut bars that we use to support it have actually bent from the weight and the temperature in the fire. The lower right-hand corner shows a copper tube that is the vapor return that has completely separated from the aluminum tubes that were feeding into that. So the temperatures were high enough to melt that joint, and there's plenty of damage. Even some of the U-bends on the A coil were melted, in some cases completely gone. So here's a picture of the fire in progress with ignition on the upper left. About 30 seconds later, and then moving to the hallway to look at flames starting to come out in the lower left-hand side, and then they're definitely in the hallway in the lower right. As it progresses, it comes out of the hallway and into our collection hood. And finally, this lower right hand is when we actually started a sprinkler in that test room, and it was pushing all of that, those hot gases down the hallway just due to the flashing of water into steam and pushing everything out of the room. So we really didn't see any significant difference in heat release or smoke or temperatures based on the leak location. There was no significant difference in the heat release rate. The heat flux was higher in the baseline test than other three. And then the temperatures at the air handler were sufficient to melt parts of the A coil. So going on to our overhaul activity, scenario 4, we had the first scenario where we were just spraying refrigerant into an existing fire. Probably didn't look anything like an overhaul condition. So in this case, we were trying to simulate a line break in the refrigerant lines occurs during an overhaul. So what we have here is we have a 5-foot little wall in the lower left-hand corner here, and that leak location, the little red star, was pointed down to the corner of that area where it would bounce and cycle around to a sand burner that we had operating at 40 kilowatts. And then there was a 1-foot gap in that for the gases to come out. We also had right outside of that gap, we had a measurement of heat flux. And in other places, we were looking for any indications of a room pressure rise, a boom or a bang or anything like that. We also were measuring the ventilation flows, and we also collected hydrogen fluoride through a solvent method where we're sipping the air that's coming out of this and then measuring the concentrations and then back calculating that to say what was the average concentration of hydrogen fluoride in the air. Down the center of this hallway was our open path FTIR source, which again we used to give us relative indications of hydrogen fluoride concentration. So again, I've still got this relative dose, but I need to divide that by the time, which I don't have on here. And anyway, you can see that the peaks for all of these refrigerants in these scenarios was about the same. So it didn't matter whether it was an A1 refrigerant or an A2L. They all had about the same average peak. And as far as relative averages, in the very last column, you can see that they were all within 2% of what would come from R410A. The peak in R32 was about 18% higher. So on the left is looking at these relative peaks. In this case, the R410A peaks right at 1, which is the blue line, and the others are slightly higher than that. Again, this average dose shows that they all climbed up to about the same levels as R410A. And then I'm showing the same thing as far as the mass release. Obviously, the most hydrogen fluoride generation occurred when we were releasing it the fastest at 50 grams per second. But overall, the climb to the overall average was steepest first, but eventually came out to the same level. We did notice some change in heat release as we were doing the discharge. Again, it was very slight. Our baseline test was our baseline before we started release was 40 kilowatts, which is at the low end of our calorimeter. So our error, relative error at this low end, because we're capable of measuring 5,000 kilowatts, and we're talking about 40 kilowatts. So our relative error is around 62%. It's about the best that we can do at this low end of the range. So don't worry about the R410A. It's probably just a relic of the 62% error rate. But you did see that there are slight increases in heat release rate. I'm gonna have to take a sip of water. So as far as the change in heat release rate, that last column shows, if you discount the R410A, the first row, it was somewhere between 12 and 17 kilowatts additional above the 40 kilowatt fire. What a good sized home gas log fireplace is about 25 kilowatts. So we're talking about maybe 2 or 3 sizes of that. It's still a pretty small fire. Now these are some graphs of what the arrangement looked like. We had heat flux gauges in the upper right hand corner, right outside that opening in this little knee wall. It was 3 feet tall and 5 feet wide, except for the gap on the side where those gases could swirl and exit. In the lower right hand side, you can see those same 3 heat flux gauges right next to the outflow or the gap. So the sand burner is in that same area. We also had a hydrogen fluoride sample probe in the center of the room, and a thermocouple tree. And going back to the upper right hand side, our discharge port was about 1 foot from the wall at the 4-foot elevation, and it was angled down to impact the corner of this little 5-foot wall. So there'd be, the intention was to knock off the speed so there'd be greater dwell time in that flame. Again, this is taking a look at what the flame looked like after we let it percolate for a while. This is 40 kilowatts. It's kind of going straight up. Then after we start the discharge, you can see that the flame is very much disturbed. Not much change in the actual heat release rate, but the visible heat release rate, obviously went down. And you'll notice that we changed the background from the white Durock board to painted it black so we could see some of the mist of the refrigerant being discharged. So you see that in the 2 or in the 3 panels that have a black background. In the R32 case, lower left hand, even though that looks like it might be some R32, it's if you see the whole video, it's really just the propane flame being disturbed by this discharge. We didn't see any visible sign that there was any ignition of this refrigerant at the sand burner. So overall, in scenario 4, the production in the hallway was much larger than what we measured in scenario 1. But again, they're not really comparable, because in scenario 1, our exhaust hood was directly over the fire. So there was everything that was produced went straight up, where in scenario 4, all the gases had to traverse that hallway. So they were in the beam of the IR for a much longer period of time, which could itself lead to a higher measure of concentration. We did notice that there was less pushover, I called it, of the burner flame indicating that we did have a lower velocity of refrigerant through the sand burner. But the change in heat release rate during the discharge was 50 kilowatts maximum, and very likely much lower than that. That was the one exception with R410A. The heat release rate is, and it's a comment that we're operating at the very low end of this calorimeter, but we needed to use this calorimeter because of the scenario 2 test going up to 2,500 kilowatts. The final test that we did is we wanted to look at what happens if we have a pool of refrigerant that's created in the test room. So what we did is we created a diffuser that would knock down the release rate and spread it down low in the room, but then we also blocked half of the height of that hallway door, so that essentially we had a pool for this dense gas to accumulate in. Actually dense and cool, because it comes out around minus 50. Again, we were looking for room pressure. We also were measuring heat flux. To measure concentration, we're using oxygen sensors right next to it, and also next to the door, because we wanted to make sure that we had fairly uniform concentrations after we finished our discharge of refrigerant. We had an electric match and a heptane cup, which we first started at 6 inches above the floor. That didn't work out so well because the gas mixture was way above the UFL for the refrigerant, R32, and there was very little oxygen present, probably less than 11%, so that we couldn't even ignite the heptane. It did smolder, but it would not ignite. So we also had thermocouples, and we had the open path FTIR. So this is a little more about how we did the diffuser. We took a piece of Durarock, 3 feet square, and elevated it 1 inch off the floor with spacers. And then we had an 11-inch hole cut in the center of it. And then we took our sand burner that we had been using to flow propane. This time we decided to flow refrigerant through it and turned it upside down over that hole. So the refrigerant, as in a liquid state, was coming into that sand burner, flashing to vapor, and then dispersing through the room through that small gap at the bottom of that 3-foot square. We estimated that our discharge velocity was somewhere between maybe a foot to a foot and a half per second, or 0.3 to 0.4 meters per second. So it was pretty slow. And again, this is an overview look at it. You can see that the hallway door is blocked with a piece of drywall. We have our refrigerant sensors there and in the center of the room. The diffuser assembly is all there. We also have a stand on the right side. We have an electric match at the 10-inch level with a 30 milliliters of heptane. And at the 2-foot level at that same location, a little plastic cup with 30 milliliters. And then we created our own special candle, which was paper towels and cheesecloth sprayed with a little bit of heptane and then wrapped in plastic just to keep the heptane from evaporating. So, you know, we had cords to actually ignite those matches. We wanted to start with the match at 10-inch level. So what you're seeing on the left is as we were first assembling the lab, but we did measure concentrations. So a summary of all the testing we did one test just to prove that we didn't have any leaks, and we did find that there was a leak, and that was patched so that it wasn't going to be a problem in the next 5 tests. So we did a concentration test with R32 and with R410A. And then we tried an ignition test with R32. We're not able to ignite at the 6-inch level. Then another test with R32 where we were able to ignite at the 10-inch level. And then finally another test with R410A. We did not see any observable propagation from that ignition. So to show you that we have fairly consistent concentrations across the room, the dashed lines are in the center of the room. Or, sorry, I need to make sure I'm reading this graph correctly. Okay, so I am showing, comparing the first test where we had a leak to the second test with R32 where we did not have that leak. So you can see that dashed line that's above 35% has some squiggles to it, and that was due to the turbulence caused by that leak at the sand burner. When we repaired that, we went much higher in concentrations at the 6-inch level, way above the UFL, about 29.5% for R32. So we knew we had a very heavy concentration at the floor. And then if you go down one level to 12 inches, you can see that we were right in the middle of the region between the LFL and the UFL. And based on this data, we decided, well, we think we can have an ignition point somewhere between 6 and 12 inches. And that's when we decided to try 6, thinking that the initial flaming of the heptane would go ahead and ignite. But we were proven wrong. So this is comparing the concentrations of R32 and R410A. Again, we're seeing, and R410A is an inflammable or an A1 refrigerant, which means it's not flammable when tested at 23 degrees C. The dotted lines that I have there, about 17 and 20%, come from R410A at 60 degrees C and pretty high humidity. So it's just showing that what we had in the room for R410A really could not be ignited, but there was definitely an ignitable mixture in the room for R32. So this is comparing now the concentrations that we had in the center of the room and at the door. So you can see that those lines nearly fall right on top of each other. So there wasn't any real gradient or change in concentration at the floor level across the room. The floor level was pretty much uniformly above the upper flammability limit. Just looking at the diffuser temperatures, it was flashing the steam. So you can see that with those red lines, the square boxes when we were actually releasing refrigerant, dropped down to close to minus 50 C. And then as the discharge continued into that lower state, temperatures started rising. And then by the end of that discharge time, we were back up to around 0 degrees on those metal surfaces on the sand burner. And here I'm looking at R32 ignition and non-ignition. So we had slightly lower increase in R32 for the ignition case, which is the one with the immediate drop at 900 seconds. The first 2 lines that are nearly overlapping each other are the R32 concentrations after we fix the leak. So, and then on the right side is R410A, and you see a little bit of a squiggle after 900 seconds, which is the turbulence caused by attempts to ignite the heptane dish. So taking a look at the R32 test, here's the temperatures after ignition. In the room center, we got up to around 450, 500 degrees C, and that's at the ceiling level, 92 inches. In the hallway, where the flames tended to migrate to, we got above 600 C. And at the hallway door, this thermocouples were on the inside of the room. So eventually those flames did creep all the way down to the floor. That was pulling in oxygen and mixing with fuel in the rest of the rooms. And that's why you see that dark blue line going up to 600 C. That's at the 8-inch level next to that door, and represents those flames growing down to the floor as it's pulling in that very high concentration of R32. And finally, in the hallway, our temperatures went above 200 C. And again, that's at ceiling level. At the lower levels, the 8-inch level saw virtually no increase in temperature. The 32-inch level got up to about 100 C. And just comparing the room temperatures, R410A and R32, again, we did not have anything like ignition. What temperature-wise we saw probably came from our attempts to ignite our different ignition sources. As far as the hallway hydrogen fluoride concentration, this comes from our IR instrument. You can see that there's an immediate peak in fluoride concentration, hydrogen fluoride in the hallway with the R32 test. It's a slower rise in R410A, and part of it is the driving force of the fire. So the R410A had less driving force, so what gases were released were slower to get into the hallway and then stayed much longer. Where with the R32, essentially there were flames coming out the door into the hallway within 70, I want to say 70 seconds of the start of ignition. So here's a look at the R32 ignition photos. The upper left is right at the point of ignition. You can see a blue flame that was expanding left and right. 1 second after ignition, it had kind of engulfed our candle flame and the cup, although it didn't stay ignited for a period of time. But you can see a ring of blue flames down at the bottom of that's not at the floor level. So it wasn't able to move that flame down to the floor because it was way above UFL. Even in 32 seconds after ignition, it's hard to tell from a flat screen, those flames that you see at 32 seconds are all above floor level, and there is a slight blue flame underneath it where it's pulling up some combustible mixture from the floor. Finally, at 36 seconds, we actually had flames going out the door, the top of the door. And at 40 seconds, we were starting to black out our camera with the smoke that was being generated. And you can still see that the flame has not gone down to the floor level. In one of the videos, we actually saw that our heptane cup at the 25 second, about in there, actually stopped flaming because it was pulling up a heavy concentration of R32 and extinguished the heptane, but then turbulent mixing actually forced the flames back down. So hopefully those will all be apparent in the firefighter training videos that are produced. This is now looking at the R410A test. And this is at ignition. At 1 second, you can see there was a slight ignition, something blue. It's unclear whether that's heptane or if it was R410A. But then at 25 seconds, all we had burning was our heptane pan. So again, at 32 seconds, nothing ever came into the hallway except some light from these sources. And finally, at the 140 seconds, down at the bottom of that picture, you can see some smoke. So what we're guessing is that the smoke layer is not light enough to rise from heat, from buoyancy, but it's too light to actually sink through that heavy gas layer at the floor level. So that was just kind of an interesting observation out of the whole series. I think that was my last slide. Well, some observations. Obviously, the high concentrations at the floor level did not ignite. The R410A showed a thick layer of smoke spreading horizontally. It was less dense than the R410A at the floor, but it was less than that of air. And I think that was my last slide. So I guess it's time for questions. And I'm going to have to see if I can pull up.
Thank you, George. Thank you so much for that presentation. I know that this project has been of great interest, and I think that folks are very much have wanted to see the results of this project, and we greatly appreciate. We know that you are working very hard on producing the report for this project, and so we really greatly appreciate you taking the time out to present this information. Over 400 people have attended this webinar and have been very anxious, I think, to hear the results of it. So I'm going to, for a minute, and then we'll get to the questions that folks are starting to populate the question and answer box with. First, I wanted to kind of turn to Dick and Bill for a minute and ask them to share their impressions around the testing. Unfortunately, because of the pandemic, not a lot of people were able to attend and watch this happening in person. Dick and Bill were kind enough to be there in person and took a lot of time to be present. So, when we first started kind of putting this project together, what quickly became apparent to me is that one of the questions that people wanted to answer was whether or not these refrigerants would behave like propane. And I think, some of those first scenarios kind of pointed to some clarity there very quickly. So I think I'm wondering if you guys could share your impressions there, and then I'm going to ask you after that to maybe talk a little bit about, not only what you saw with the first couple of scenarios, but then what you saw that made you feel like we needed to add a scenario, that's scenario 5, and then maybe we can talk a little bit more about what you saw with scenario 5. So first, maybe you could talk a little bit about your impressions, or maybe what you were hoping to see or hoping to learn with that initial testing, and then we can go from there.
Thanks, Helen. This is Bill Offerman. When I was asked to join the panel, our concern was that this was going to react similar to propane, natural gas. We were going to have explosions, significant damage to residential property, commercial property, that our firefighters were going to be in danger as they enter a structure because of the release of this gas. So the tests were based around a lot of those scenarios. What were we going to come into? How are we going to have to work around the various products that are being tested right now? And how are they going to react to a flame, an ignition source? So I think that we covered the majority of those bases. If you want to talk about those in just a minute, Helen, I'll defer to Dick for a moment, and then we'll continue through.
Sure. This is Dick Lord, carrier, and I was there with Bill kind of watching these tests. I mean, it confirmed a lot of things that we kind of knew. We've been working at these refrigerants going on 10 years. We developed the 2L category because we know these refrigerants are not like propane. Propane is a category 3 refrigerant. And it basically confirmed a lot of the things we know. It confirmed that yes, any of these refrigerants can make HF. So, all the precautions that are on safety data sheets and, the firemen are well trained on, those apply to both A1s as well as A2Ls. And, we'll talk a little bit about scenario 5, some of the observations there, but I think it confirmed a lot of things that we were trying to explain. I mean, I learned a lot about firefighting and, what the concerns you guys have. So I think it was a good cooperation between us and the fire services.
Great, thank you. I think, let me ask you a little bit, I see one of the questions here around hydrogen fluoride gas, so, and NHF acid. So there was one addition that I asked for, and UL was kind enough to add it in right at the last minute for me. One of the things that we wanted to understand better with this testing, and George, I may ask you to chime in about this one a little bit as well, but one of the things that we wanted to understand better was what's the difference from an HF hydrogen fluoride gas and HF acid production between the current refrigerant R410A and future refrigerants. And I think, George, if I'm understanding correctly, and I know that you're certainly still working on the report and crunching numbers, but there's not much difference between the amount of HF that's generated. It's more, it's more of a concern that we need to remind people of, not only from the fire safety first responder perspective, but also technicians that are welding on equipment. You can produce HF today. You can produce it tomorrow. It's important for you to understand it, and it's really important to protect yourself. And the very wonderful thing that the UL team did at the end of the testing is they did check to see if there was residual hydrogen fluoride on surfaces after the testing was complete, and it was present. And so it's something that we want people to be aware of, that decontamination needs to take place before folks dress down, and remove their personal protective equipment. So George, any other comments around, the HF and maybe the differences between 410A, the current refrigerant, and the future refrigerants, if there's anything, that we learned that might be of interest to the folks here today?
Sure. The biggest thing we saw that I couldn't put in this presentation was the results of the bubbler method, where we're sipping the gases in the hallway and in the room. We weren't able to get those analyses completed before this presentation was made. But obviously what we did find was in that scenario number 5, where we had that ignition of R32 and not with R410A. It's a huge difference. So, definitely under some circumstances, you can get far more hydrogen fluoride production from R32 or these A2Ls that are somewhat ignitable than the R410A. But in all the other cases, they're very comparable.
That's very helpful, George. I mean, I think what I learned from this is that, and I guess it's kind of intuitively obvious if I think about it, but, it's more about how much decomposes or combusts rather than which refrigerant you're looking at, right? And it depends on the situation. The first 4 scenarios were produced very similar results. The last one, there was less combustion taking place of 410A, and so less HF produced in that situation, more on the R32 side, so more combustion taking place and more HF generated there. And so to me, it just says it's very specific, but I don't know how you would know what you're walking into, and so you really need to be prepared in either instance, because you don't want people that are exposed. George, that's kind of my takeaway on this. Am I maybe misunderstanding or misinterpreting that at all?
No, I don't think so. We've demonstrated that HF is going to be present regardless of the refrigerant.
Thank you, George. I'm going to turn back to Dick and Bill. So you all sat through hours and hours and hours of, kind of in between testing setups and during the testing, and kind of had some time to talk a lot about A2L refrigerants, but also about, kind of what you wanted to see. during the testing process, you all decided that you wanted to see another scenario run, and that was scenario 5, and that was added on, kind of during the process. We had, all agreed to run the first 4 scenarios and then added this 5th one on. And could you maybe talk a little bit about what you all wanted to see with that scenario and what you feel like you learned? Did you learn what you had hoped to learn from that?
I think we covered the bases on that. When we started with the original scenarios, it was more of the firefighters' response. What are we going to come into? Are we going to have a leak in a line? Are we going to have a leak in a unit? Are we going to have a severed unit during overhaul and the line is actually ripped out and we have a big dump of product? So we actually did the constant releases at 6 foot. We did constant release. I think there was 1 or 2 of them at 4 foot. Then decided we'd do some at 2 foot as well. And then we also did decaying. Because we realized that as that product was released, it was very cold and it was also a very high concentration. So we wanted to slow that down, warm it up, and get more into the LFL and UFL area to where we'd actually might have some flame propagation from it. So we actually did all 4 of those with the decay as well, 3 of them, so that we could get into that area to see just how much it would ignite to make sure we didn't have an explosion or anything. And we did not. So that was good. Then we had a discussion about what if we have a unit that actually leaks into a small area. We don't see it, we can't taste it, smell it, see it. We come in there, start pulling some materials, and we drop a flame into that. Are we going to have a major issue with that room? So that's where scenario 5 was developed from. But then we actually had to put into place the sand pit in order to slow this down enough, warm it up enough to get a mixture to where we could actually ignite it. It actually took a lot of work just to get it to that point. So I was a little surprised with that. I expected it to be much more readily combustible. And then once it did ignite, it was more of a wisping flame, and it wasn't a rapid expansion. It wasn't a rollover, it wasn't a flashover. So I think we were successful in testing for what we were looking for.
I mean, maybe add to what Bill said, one of the things that, a lot of people have had concerns about, the refrigerants are odorless and colorless. I mean, you did see the refrigerant cone when George was showing the first test. That's really not the refrigerant you're seeing. It's actually the moisture in the air being condensed out of the air because these refrigerants are at -50. But, we made a rather extreme test in scenario 5 just to confirm this. It has basically twice the amount of charge that we allow in the standard. So we got to almost 50% LFL or 50% of the LFL in that whole room. And, these refrigerants are heavier in air, so we wanted to show the concentration on the floor. And it was, actually, I found that test very interesting because, we were able to ignite the refrigerant, but it didn't propagate through the room. Actually, the refrigerant moved to the flame, and then you see it kind of going towards the door. And George helped me understand that as it's seeking the oxygen that's at the door. So, and it kind of went along with Bill. It's not a very rapid progressing flame that, was something, I'm not a fireman, but it's something that looks like it's reasonable, people could understand. Very difficult to create that scenario. I mean, you had to have a tightly sealed room with no air movement, with nothing going on to get that concentration in there. So I think it was a good test, and I'm kind of glad we added it. It gave some more demonstration of what we can see with these refrigerants.
Thank you both. I'm going to pivot and ask another one of the questions that folks have put into the feed. They're asking about kind of storage and handling, and we're going to provide some additional information about that in one of our future webinars. But Dick, any comments around that? What do people need to do in the same way with these refrigerants versus maybe do differently in kind of storage and handling of refrigerants?
Yeah, sure. I mean, one of the things we did, and when we developed UL 60352-40, and we've talked about it in 15 and 15.2, is, service practices. So, with any refrigerant, and this is, our whole industry needs to improve on this, you really should reclaim refrigerants. They're global warming gases. We shouldn't be venting them to the atmosphere. And so there's a lot of procedures we've developed. What we've recommended in there is you pull the charge out into a proper reclaim vessel with proper reclaim equipment, and then purge the system with nitrogen, which they should be doing anyways. Like if you're going to braze on a system, you really should purge with nitrogen because you make copper oxide. So, as you get into 2-40, I know the servicemen won't read that standard. All of it will be lifted and put in our service literature. We've already done the NATE exam training. So one of the things we're going to be focused on this year, and we'll probably include in some of the fire service training, is all the work that we've already done on service and how you handle these new refrigerants.
Thank you, Dick. George, I'm going to come back to you, and somebody's asked about the fuel source in some of the testing, so I'm going to come back to you in a minute. I did want to let people know that the reason for doing this project was to respond to a need for for the fire service and for training there. And so all the videos, well, there's so many hours of it, you probably couldn't put them all in, but those videos will be selected to add to a training program that will be live on the internet for viewing. It'll be free of charge. The Fire Service Research Institute is going to put that training program together, and we'll provide additional information to them as needed, and certainly they can pull from all of our research project reports, which are online and available for anybody to look at. So that'll be available in the second quarter of this year for anybody to take a look at. FSRI does a wonderful job, and very interesting to go on that website and take a look at what they do. So and once that's done, we'll pull folks back together. We'll let you know if you'd like to come back to a webinar and kind of see what that training, kind of have a sneak peek of that training. George, I'm going to pivot to you and ask you about the fuel sources. Somebody was asking about the fuel sources. I think they were interested in what's in the boxes, as well as what kind of a fuel was used for the fires and the other scenarios. If you could maybe talk about that a little bit.
Okay. Yeah, I think I'm unmuted. The boxes contained 5 levels of cardboard spacers with plastic cups. So there were 25 cups on each level, stacked 5 high, in a cardboard box. It's pretty much standardized. I think burning one of those boxes by itself produces about 250 kilowatts in a free burn all by itself. So it's commodity, I think our technical term is commodity classification type A, if I got that right. I'll definitely have it in the report. I don't myself do a lot of sprinkler testing, but that's where those boxes come from.
Thank you very much for that, George. Bill, I'm getting text questions now. And one of the questions that I'm getting is, I'll give you a minute to think about this, but whether or not you feel like you've got enough information to kind of know how to handle this situation, and and certainly in the development of the training, if you feel like there's enough information now readily available for that training program to be developed. So I'm going to ask you that question here in a minute. In the meantime, Dick, I just wanted to double check with you around again, a kind of a question around the HF. I mean, we have seen a lot of research done in the past around HF, and certainly, everything that I've seen from the auto industry, as well as things that have been done in other situations looking at HF, have kind of yielded similar results, that the HF production can happen with any, even with fire suppressants, and certainly, it kind of depends on a little bit on the ratio of hydrogen to fluorine. And I'm just wondering if you could maybe speak a little bit to that, and kind of what you've seen in the past, and if there's anything different from this study, or if it really just kind of confirmed your previous knowledge around HF generations related to fluorocarbons.
Sure. I mean, we kind of knew it, we're very much on the technical side that, all these refrigerants make HF. And when you look at the safety data sheets, when you look at the A1 refrigerants, most, if not all of them, make HF. I think it's one of the things as an industry, we really haven't done a good job on educating. So, one of the things we're talking about is, we need to do more education, point people to the safety data sheets. I think the firemen understand that, but, maybe not some of the service people and things like that. So that's one of the things we're talking about focusing on. And, we got the Safe Transition Task Force that's working on that. And you're going to see a lot of communications coming out of us just to educate people on, these refrigerants. And I know Bill knows this. I mean, there's a lot of strange things that show up in fires. And so, I mean, his people understand, but I think we need to educate our whole industry.
Thank you, Dick. I'm gonna ask Bill now the question around, do you feel like you have the information that you need? Is there, do you think there's enough here to kind of put together this training program to provide other fire service professionals with the information that they need to be safe around these refrigerants? Do you feel like your questions have kind of been answered?
My questions were answered. I'm very comfortable with the flammable issues. However, I have not seen the test results for the HF, and I'm very concerned about HF and what we need to do. And we definitely need to focus on putting together a significant training program to get the information out on responding and working on this type of a product where it may leave a residue of hydrofluoric acid.
Great, thank you, Bill. So folks, I've got one other question that's very, very broad. Somebody asked kind of very broadly if there's any conclusions or recommendations out of this. And I think that we've heard, kind of about the HF concern. But if there's anything else or any last words, I know we're kind of running out of time here on the webinar. But let me put it to you all. Dick, maybe I'll start with you, and then we'll ask George and Bill if they have anything that they'd like to add.
Yeah, maybe I'll start off. I mean, it confirmed a lot of the information we've done. We've been doing a lot of testing through AHRI. As Steve said, we've done about $7 million worth of testing, and that's just AHRI. I think all of the manufacturers have done testing themselves. I think we know what we have to do. We've got a lot of education to do between now and when we first start putting these into production, which most likely will be 2025 now based on the newest regulations. So we got a lot of training to do, but it's an environmental responsibility. We're not doing these refrigerants because we just like changing refrigerants, but it's a global responsibility. We need to do something for global warming. So, it's a transition we're doing, and we just need to educate people and spend a lot of time now in between production on the service training, the fireman training, and looking forward to getting some of the training that UL is going to do, as well as some of the industry training groups that are going to do.
Thank you, Dick. George, any conclusions or recommendations that you'd like to share with the group? This is kind of a really broad question, so.
Yeah, extremely broad.
Yeah.
One term that I've been trained in my time working at UL is we try and stay away from the phrase, we just finished a worst case scenario test. Whatever we could possibly design, you could probably come up with something else. But as Bill was pointing out, it took some design to get that one fire test going. And I know we've had some other fires in the past in previous AHRI studies where we did see some more energetic fires, but it was done at 90 degrees and almost 70% humidity with lots of obstructions knocking the flow down and a very energetic fire source. Is that the worst case? Probably not. You could probably come up with some other design. I think we've bracketed the whole thing with this study and the earlier AHRI studies.
Thank you for that, George. Bill, any comments that you'd like to make, or any thoughts that you'd like to wrap up with?
Certainly. We live in an ever-changing world, and we work in an ever-changing environment. So whether this is architectural, whether it's chemicals, whether it's transportation, we have to learn about what we have to respond to on a daily basis and adapt to that. This is just another step in that. It's our responsibility now to take time to read about this, to learn about it, to educate our folks, and to keep ourselves safe as well as the public. So it's time for us to take that next step, and with your folks' helps, we can put that training together and get it out to everybody.
Thank you, Bill. Really appreciate that, and I appreciate all the panelists joining us today and sitting through. I'm going to tell what kind of a geek I am. I'm jealous that you guys get to sit through all that, but thank you for sitting through all of the countless hours of testing, and George, all the work that you've been doing to finalize this report. It is very, very much appreciated. Folks that have joined us today, we really appreciate your attendance. This webinar will be placed online. We'll provide you all with a link to that. if you registered for it and signed in. In addition, we will be pursuing continuing webinar series. Next month we'll be coming together again, and you'll receive information about those webinars as well. So thank you again for joining us, and we hope you all have a very good evening.
Thanks, Al.